so far, all we've talked about was IPv version 1, right? So IP version 1, Internet Protocol version 1. I'm saying version 1, but I mean version 4. Well, we also have IP version 6, so Internet Protocol version 6. And what we're going to do here is we're going to go over the differences between the two. So IP version 4 is made up of 32 bits. So that's 4 octets with 8 bits each, right? So those 8 lanes. So 8 lanes, 4 times, is 32. Meanwhile, IP version 6 is made up of 128 bits. So there's 8 segments with 16 bits in each one. 8 times 16 is 128. So IP version 6 uses hexadecimals, just like MAC addresses do. Hexadecimals basically means there's going to be letters that we're going to use, and those letters are going to represent numbers. And that just makes it so it's easier for us to read, right? Because we're humans and not machines and robots. So A is 10, B is 11, C is 12, D is 13, E is 14, and F is 15. So here, 15 is the highest hexadecimal number. So remember, we said there's 16 bits each. That's because we count 0. So 0 to 15, 16 bits. So we can break down each of these numbers. So this is what IP version 6 IP address would look like, but we're going to break it down into 4 binary bits, right? So these 4 binary bits make up the first segment. The colons here represent each segment. So this is segment 1, this is segment 2, segment 3, segment 4, segment 5, 6, 7, and 8. Okay. Now we can shorten this IP version 6 address. But you know what? Before we do that, let's look at this here. If we're breaking down this segment, notice how we're breaking down the segment into 4 like mini segments, right? And this just helps us to be able to calculate the numbers here. It makes it easier for us, because instead of saying, oh, we need 4 times 4, we need 16, right? Because this is made out of 16 bits, as we mentioned here, 16 bits. We're going to break that down to 4 segments of 4. 4 times 4 is 16. 4 segments of 4. The first segment, 16 bits here, but we're going to cut them down to 4 to make it easier for us, right? So here we have 0, 2 raised to the power of 1, which is 2 here, and this one's on, right? So 2 raised to the power of 0 is 1, but this one's off, so it's not a 1. 2 raised to the power of 1 is 2, and this one's on, so this is number 2. All of them are off, 0, all of them are off, 0. 2 raised to the power of 0 is 1. So remember, we're doing the binary lanes, but we're only using 4 binary lanes. So 2 raised to the power of 1, 2 raised to the power of 2, well, 2 raised to the power of 0, 2 raised to the power of 1, 2 raised to the power of 2, 2 raised to the power of 3. So that's how we're getting these here. So this is how we figured out this segment, by breaking it down to 4 mini segments, each with 4 binary lanes instead of the 8. All right. So we can shorten this IP version 6 address too, the way it looks. So notice here how we got rid of a bunch of zeros, right? Only zeros here. Well, if there's more than one segment of zeros next to each other, you can shorten the way the IP version 6 string looks by using 2 colons to represent the zeros. You can only do this once, though, starting from the left of an IP version 6 string. So if there are any other 2 segments that were all zeros, we couldn't replace them with 2 colons. So let's dive deeper into how we can shorten IP version 6 addresses. There's 2 steps. So step one is to get rid of the leading zeros, right? So here's the IPv6 string. We're going to find each of the segments that start with a 0 and remove them. So here's the new shortened IPv6 address, right? So if they start with a 0, you can remove that 0. Start with a 0, remove that 0, right? These are all the segments here that were shortened by removing the leading zeros, right? So zeros in the front. If a segment is all zeros, oh, by the way, yes, one number must remain in each segment. So in this case, even though we got rid of all these leading zeros, we still got to leave 1 0 here for now, right? We got to figure this out. So this is the first step. If a segment is all zeros, keep one number in there, so we keep the 1 0. Step 2, we're going to look at the 0 segment neighbors. So here's our IPv6 string, right? That was already shortened. So we shortened it one time already for step 1. Now it's going to be step 2. And here we're going to look for what I call 0 segment neighbors. So for those neighbor segments, we can replace those with 2 colons. See? So we got rid of the 0 segment neighbors with 2 colons. So this is what our IPv6 looks like now that the leading zeros are gone and removed, the zeros in the front, and the 0 segment neighbors are replaced. See, we replace the neighbors with the 2 colons. So notice that the leftmost 0 segment neighbors are replaced, but not the second set of 0 segment neighbors. So all 0 segment neighbors after the first set of 0 segment neighbors remain the same. They don't change. So it's like you have one special power move and you can only use it once. So you can use it on the leftmost one, but the other ones you're not going to be able to do. So just like IP version 4 addresses, IP version 6 also uses a type of mask to separate networks and identify the host portion of IP address and a network portion of an IP address. So the /64 is used to tell us how many bits are blocked for the network portion of the IP address. So remember how our segment is 16 bits? If there are 64 bits being used for the network portion of the IP address, let's count to see how many segments make up the 64 bits, right? So this is 16 bits, 16 bits, 16 bits. So this 16 times 1, 2, 3, 4 gives us 64. So this 64 bits is known as the network prefix, right? Because we're looking for 64 bits. This is the 64. Yeah, so the network, so what we used to call a network mask in IP version 4 is called a network prefix in IP version 6, but it's essentially the same type of thing. Using this prefix, we can find the available range of addresses. So we know that 64 bits are part of the network portion, right? So those will not be changed, leaving the rest of the segments open. If all the segment bits were turned on, we get 1 plus 2 plus 4 plus 8, which equals 15. And 15 is represented by F for each number in the segment. So that's why we know the highest number for IP version 6 is 4 Fs. Any segment, the highest is 4 Fs because it's 15 each time. So just like 255 was the highest number in IPv4, these 4 Fs is the highest in IP version 6. So we can use our IPv4 subnet mask shortcut for IP version 6 prefixes too. we know that the highest string of IPv6 is 128, right? So if we subtract our 64-bit prefix from the 128 possible bits, we get 64 bits, right? Does that make sense? So 128 possible bits for this whole string. We're using up 64 for the prefix. So 128 minus 64 gives us 64. 64 can be either on or off, right? The bits can be either 0 or 1. So we raise that to the power 2. If we do that, we get the possible case here of available IP addresses, which is 184 quintillion, 466 quadrillion, 744 trillion, 73 billion, 709 million, 551,616 available addresses in the network range for IP version 6. And as a note, there's no need for a broadcast address for IP version 6 because they use multicast addresses, which sends data to a group instead of everyone. So for an example, FF02:2 sends to all routers, right? Multicast addresses are built specifically for specific targeted versions of broadcasts. So there's like all routers and all switches and things like that. It's very specific. So they have specific addresses. That's why we don't need a broadcast address. So what about public versus private IPs? So almost all IP version 6 addresses route over the internet as they're all unique, like MAC addresses. So internet service providers usually assign these IP version 6 addresses. As for private IPs, IP version 6 IPs, the only private ones are IPv6 addresses that are in the FCC00:7 range. So those are the only IP version 6 addresses that can be routed, that can't be routed over the internet. All the other ones can. Just the ones in this network cannot.